This article is similar to the previous article, kinetic energy of rotating body and angular momentum. So we consider here a rigid body made from n number of particles rotating about an axis with angular acceleration alpha. So this is body made from n number of particles. The first particle having mass m1, distance from axis r1, and the force acting on this particle is f1, and the acceleration of this particle, linear acceleration, is a1. Second particle, mass m2, force f2, distance r2. Third particle also we can show somewhere. Fourth, fifth, sixth, the nth particle, mass mn, force fn, distance rn. Now the procedure is similar. Now we find out torque acting on first particle. Torque formula is force into distance, F into R. So it's the first particle, so we can write F1 into R1. Now by Newton's second law of motion, we can write F is equal to ma. For first particle, so F1 is equal to m1 a1. So that we substitute here m1 a1, this R1 as it is. Now next step, this a1 we can write. So you know that A is equal to R alpha, relation between linear acceleration and angular acceleration. So it's the first particle. So A1 is equal to R1 alpha. So we are not writing here alpha 1 because alpha is same for all the particles. So here we get this step. Now R1 square. So we get torque acting on first particle and it is M1 R1 square alpha. Similarly, torque acting on second particle, torque 2 is equal to F2 R2. Now here F2 we can substitute M2 A2. Then, so here we substitute F2 is equal to M2 A2. Then after that, again A2 is R2 alpha. After substituting that and solving this, we get torque acting on second particle and it is M2 R2 square alpha. Similarly, torque acting on third, fourth, fifth, and the nth particle we can write. So torque acting on nth particle. So torque acting on nth particle is Fn Rn. So that Fn we can write Mn An. Then An we can write Rn alpha. So here we get torque acting on this nth particle is Mn Rn square alpha. Now torque acting on body is addition of all the torques. So torque 1 plus torque 2 plus torque 3 plus ... torque n. Now we substitute the values of the torque. So we get here alpha common in every expression. So we can take alpha common. So as we take alpha common, inside the bracket we get this term, and this is summation mi square. And this is nothing but the moment of inertia. So torque is equal to moment of inertia into angular acceleration. And this is expression for torque acting on rotating body. This derivation is also asked in the board